Okay, so this video is going to talk about how you can propagate error using thermobar. Specifically, we're going to be looking at clinopyroxene only and clinopyroxene liquid errors. So this is described in another video, but on Read the Docs, navigate to error propagation, Cpx-Liq. Click on here, press download. Click on here, press download, and put these somewhere in your computer where you can easily navigate to them in the same folder. So that's what I've done here. So I'm just going to open up this file, and then I'm just going to show you what the spreadsheet we're reading in looks like. So this is experimental data from Ferg et al. 2010. So each of these rows is a single experiment. And basically for the liquids, you have the oxide name _liquid. Then of the same for the CPXs. And then we've also loaded in, and we'll use this later, is the 1 sigma error of the experiment. So say they measured 5 liquids, this is the variation seen in those liquid compositions in weight %, and this is the same for CPX. You can see it says CPX_error. So first thing we're going to do is, if you haven't installed thermobar, you need to do so by removing this hash. Otherwise, import all of the Python things you need. And then firstly, we're going to load in this spreadsheet and tell it the sheet name. And this is literally just loading in the mineral compositions and the liquids for now. It's ignoring the errors. Should check that these inputs are reasonable. So you can see here, check any columns with zeros that was actually missing in your original data. And then we're going to do some error propagation. So to start with, we are going to basically consider error in a single parameter for Cpx-only and Cpx-Liq barometry. Say we're interested in how the error in the sodium content of the pyroxene is affecting calculated pressures and temperatures. Now, if we want to simulate synthetic CPXs and liquids, we need to make sure that the resulting data frames, or the data structures, are the same length for both if we want to do Cpx-Liq thermometry or barometry. So first off, even though we're not going to add any errors to our liquid, we're going to use the pt add noise function. We tell it our liquid compositions. We say we don't want any noise added, so that's why this is 0. And importantly, we want 1,000 duplicates. So that means for every row we loaded in from Excel, we're going to make 1,000 synthetic compositions. In this instance, because the noise percent is 0, they are all going to be identical. We do the same for CPX. But now we are specifying a variable, so specifically the sodium content. We want to add an error of 5 to this, and in this case, we've specified that this is a percentage error. So this adds 5%, sort of a 1 sigma error of 5% of the measured quantity to every single row, and we make 1,000 of them. So this will basically produce 1,000 compositions per row, so 7,000 compositions total. And you can see here I am taking this synthetic data frame. I'm interested in plotting the sodium content. And specifically, I want the sodium content rows where the sample ID of the CPX was 0. So that's the first row you inputted into your spreadsheet. So you can plot this. And this is what the simulated distribution of sodium in the CPX looks like. This is a plus or minus 5% error of 1 sigma. Okay, now what we can do is we can take this synthetic data frame, 7,000 synthetic compositions, 1,000 for each sample, and we can calculate CPX-only pressures and temperatures to start with. So here we're using equation 32a of Peterka and 32d, and we can calculate it. So now what we can do is we can make histograms for every single CPX. So we're using the same lock function as above, so we're interested in this calculated data frame, but only where the sample ID of the CPX was 0 for the first plot, so that we're plotting on this figure part AX1. For AX2, we're interested in sample ID 1, and so on. You could write this in a loop if you're more comfortable with Python. I'm just writing this out explicitly to make it more clear. So basically, this shows the distribution of pressures that you would calculate using CPX-only thermobarometry for CPX1 just because of a 5% error in sodium contents. You can see that the distributions are a bit different for every single CPX. So say you don't want to plot, like say you have 100 CPXs, you don't want to plot all 100 of them. So we also have a function, avnoise sample series, and this basically will calculate statistics for every single row. So the first thing you have to tell it is what calculations you want to average. So in this case, this is the statistics for temperature. So we've inputted the calculated temperature data frame, so what we calculated here, and we're specifying that the column we're interested in is calculated temperature. You then specify sample IDs. This is how it knows what to average by. So it's going to average all of the rows with the same sample ID. And in this situation, that sample ID was stored as sample ID CPX number, and you can see that was used up above as well. So here you go. You can see that the mean temperature calculated for the first row was 1,504 Kelvin, and the standard deviation was really, really small for temperature, 0.66 Kelvin. So that's not really anything to worry about. Do the same for pressure. So again, it looks exactly the same, but we've just put that the calculation we're now interested in is p kilobar calc. And you can see that the sort of standard deviation for pressure is about 0.18, 0.11, etc. So you can look up and you can kind of see, yeah, that looks reasonably reasonable based on what we calculated up here. So if you're considering your 2 sigma, say you would multiply that by 2, for example. Okay, let's do the same for Cpx liquid. So now we enter our Cpx data frame that's synthetic. We also have to enter that liquid synthetic data frame we made and specify equations for pressure and temperature. So again, we're now plotting each sample based on the Cpx number on different plots. So you can visualize what your spread of pressures is here. You can calculate the statistics, and now you see there's a lot more variation. So Cpx liquid, this particular one is much more sensitive. So kind of your standard deviation for temperature is now about 2.4 degrees. It's still not that much. And for pressures is about 0.2 to 0.3. This might not seem that much. You need to check your microprobe, what your error actually is in sodium. 5% is an extremely low error. Most analyses are more like a 20 or 30% error. So you can mess around with what that would do to your standard deviations. The other option is, say we don't know the microprobe conditions that we used in this study. So the closest idea we kind of have to the error is these published 1 sigma values. So these are here. This is the standard deviation of repeated experimental measurements. So we're going to now load these in using the import Excel errors function. So this is basically looking for columns with underscore phase name underscore error. So you can pull out the things with Liq underscore error and Cpx underscore error, and then we just want to inspect them to make sure that thermobar has found the right column. So looking for columns of 0 that are unexpected. Okay, and now what we want to do is we want to make synthetic compositions again, but now both the liquid and the Cpx could have an error added to it. So we specify for liquids the phase compositions we measured. So this is the liquid data frame we loaded in above. We now specify the second data frame of errors. So this means for every oxide and every row there is a defined error. We now tell thermobar these are absolute errors. These are no longer percentage errors. We still want 1,000 duplicates, and we want the errors to be distributed normally. Exactly the same for Cpx. You can see it's printed that it has replaced negative numbers with zeros. You can override this by setting positive equals false. You just need to make a decision about whether your probe would output negative numbers or not, for example. Now we can calculate Cpx liquid pressures, temperatures, again giving these new data frames as the compositions, and using equation 31 and equation 33. And as always, we can calculate statistics. So now using those sort of experimental errors, the standard deviation for the temperature is about 10 to sort of 20 Kelvin. And for pressures, the standard deviation reaches up to kind of 2 kilobars. So this is, reasonably significant. We can plot, say, for sample 0 and sample 3, what the distributions of pressures look like. We can see this is really starting to span a significant amount of the crust based on those experimental errors. Here we just do the same thing, but we're plotting for 6 different pairs. So you can see again, a fair bit of variation between how different samples respond. We can do the same for temperatures. So we can see how much the calculated temperatures vary. we can sort of inspect the statistics and we might want to plot these as error bars. So basically here we're saying that the x value is the mean of the simulation, and then we're plotting plus or minus 1 standard deviation. So you can look at this and you can basically use this to visualize how big your errors are. And we really recommend you do this. And we've got a paper coming out hopefully soon showing how important this is for CPX barometry.